Well, hello and welcome to Math 315 on analysis and topology, and this is the third recording for chapter 5. So I've introduced two theorems, intermediate value theorem, and we've introduced the min-max theorem. And remember, the conditions for the min-max theorem was that our function f had to be continuous, and it had to be continuous on a closed interval on the real line, and given those two conditions, then the function f is guaranteed to have a global maximum and a global minimum. So I'll just do a few more examples of this. So we're going to find the min and the max of this function, absolute value of x times absolute value of x plus 1, on the interval between -2 and 4. And here is the solution to this. So again, it's good to draw pictures of all these things, so I'm going to unpack this function a bit and then try and draw a picture of it. We're only interested in the interval between -2 and 4. Well, firstly, if x is positive, let's just think about x being positive for the moment, then the absolute value of x is just equal to x. And if x is bigger than 0, then this is bigger than 0. In fact, it's bigger than or equal to 1. And so this is positive. So I can take away the absolute value signs if x is bigger than or equal to 1, and I just get x times x plus 1. Now similarly, if x is less than -1, then this is negative, and so the absolute value of a negative number is -x. But this one also is negative. If x is less or equal to -1, this is also negative. So when you take away the absolute value signs for x less or equal to -1, then you'll get -x times -x plus 1, which again is just x times x plus 1. So it just looks like this in the case when x is bigger or equal to 0 or x is less or equal to -1. In the case where we're in between 0 and -1, then this will be positive, but this will be negative. And so the absolute value of a negative number is minus that number. So I'll get 1 minus here, and I'll get -x into x plus 1. So that's what this function looks like once I unpack it. And now I'm just going to draw the picture of it to help us find our global max and min. We're guaranteed, well, this function is continuous, and this is closed, so we're guaranteed it's got a global max and a global min. So it's looking like, if we just think of this one firstly, it's looking like a parabola cutting through 0 and -1. So the graph is looking something like this. And so if x is bigger than 0, I can draw this much of the parabola here. And if x is less than -1, I can draw this much of the parabola here. And what's happening in between is we're getting minus the parabola. So instead of going down below here, this little piece of the parabola will get reflected up here. So that's the graph of the function, and we can work out some various values. At the extreme values at -2, if we whack -2 into here, I just get absolute value of -2 is 2, and then -2 plus 1 is -1, so absolute value is +1, so I just get the value 2. At the other extreme, at 4, you just put 4 into here. So you get 4 times 5 is 20. So this is, I haven't drawn it to scale, so this is going to be 20 here. Now, it goes through 0 and -1. And if we look at where we're not really interested, well, we are. We need to know how high this is going. So, because this might have gone up here somehow. Might have gone up here, so we've got to check this as well. So we take the average of the two roots, which will be -1/2, and if you plug -1/2 into here, then you'll end up with, I'll leave you to check, you end up with, so 1 -1/2 is 1/2, times 1/2, you'll get 1/4 here. So you get 1, you'll get 1 -1/2 is 1/2, and you'll get here the absolute value of -1/2 is 1/2, and so you'll end up with 1/4 here, which is quite low. It's certainly less than our 20. So So we can read off then, this is going to have a global maximum of 20, that's the point over here, global maximum of 20, and at x equals 4, and a global minimum, well the smallest it can ever go is 0, and that happens at two different places, so it's got a global minimum at x equals of 0, at x is 0, or x is minus 1. Second example here is to find if they exist, and that's the important point here, the min and max for the function f of x is sine x on the open interval pi on 2 to pi. Now sine is continuous everywhere, but this interval is not open, so it's not closed, it's an open interval, so there's no guarantee. It may have a max and min, or it may not, but there's no guarantee from the theorem that it will. You can only do this by looking at the picture of it, and so I've done that here. And here's the graph of sine x. So sine x would normally come up like this and then continue on. We're only drawing it on this open interval between pi on 2 and pi. So this of course would be 1 if it reached there. So it's an open interval, and so we've got open circles here. So it's got no global maximum. It's trying to get closer to 1, but it never actually gets there because we've excluded pi on 2. So there's no global maximum, and there's no global minimum because I've excluded pi, and so there's no global minimum for this one. And that's no surprise because the theorem can't be used here because we have an open interval. Now we're going to move on to a slightly more difficult little piece of mathematics. This is called uniform continuity, and this is a little bit harder. You'll see that the sort of problems I will expect you to be able to do are not quite so difficult, but we'll have a look as we go on this idea of uniform continuity. So I'm going to consider the function f of x equals x squared on the real line to motivate this. Now we've already looked at continuity, and so this is a continuous function, and so I go back and I try and use my epsilon delta definition to look at continuity of this. To show f is continuous at some point x naught, well again we take, given epsilon bigger than naught, we suppose that we have a point x naught which is within delta of x, and I'll tell you what delta is in a moment. So we take x minus x naught less than delta. So we're trying to prove this is continuous at x naught, so we look at x minus x naught less than delta, and I'll tell you what delta is at in a moment. And as we did before, we're going to look at, suppose that for the moment delta is less than 1. Now in that case, I want to look at x plus x naught. We'll see why in a second. And to do that, we subtract, because we know something about x minus x naught, so I'm going to subtract off x naught, and then I've got to add 2x naught to make up the difference. I can now use the triangle inequality and say that's less or equal to x minus x naught plus twice the absolute value of x naught. And now we supposed here that this delta was less than 1. So this bit here is less than or equal to, or if you like just less than, 1 plus twice the absolute value of x naught. Okay, so we've established that fact. Now we have to look at the difference between the function at x and the function at x naught. So we look at absolute value f of x minus f of x naught, that's x squared minus x naught squared. Difference of two squares, we can factor this as x minus x naught, x plus x naught. Now you see why I worried about this term here. That's why we did this here. So I can now get a bound on that one. X minus x naught's less than my delta, and this one is less than 1 plus 2x naught. And as we did before, once we've got it down to here, I can now say that's less than epsilon. I put this equal to epsilon if you like, and that means delta then is whichever is smaller, 1, to make this bit here work, or epsilon over 1 plus 2x naught. So we can choose delta now to be the minimum of these two. Now that proves that this function x squared is continuous everywhere on the real line. However, the problem with it is that the point to note here is that our choice of delta depends on both epsilon, it's got an epsilon in here, and on the x naught. So it depends not only on the width of my epsilon band, but it also depends on where my x naught is. Depends on where my x naught is. If I now redo the same problem, but this time I'm going to restrict the domain of f to, say, the bounded interval 0, 3, well, in that case, if the biggest x naught can be is 3, then 1 plus 2x naught, the biggest that can be is 2 3s are 6 and 1 is 7. In that case then, putting that back up into what we did up here, that says if I've got x minus x naught's less than delta, then my f of x minus f of x naught is less than 7 delta. And so my delta now is just the minimum of 1 and epsilon over 7, and it doesn't matter where my x naught is in this interval. The choice of delta is independent of my x naught. So in this case, delta depends only on epsilon. That means it's independent of x naught. Now, functions that have this kind of special continuity, this is called uniform continuity, and this is going to motivate our next definition. So f is defined on some subset of the real numbers. We say that f is uniformly continuous on A if the following condition holds. For any given epsilon bigger than naught, there is a delta bigger than naught, and that delta can depend only on epsilon, nothing else. So that if I take any 2 points inside my set A, and such that x1 minus x2 is less than delta, then f of x1 minus f of x2 is less than epsilon. So it's like our continuity definition. In fact, it's exactly the same as our continuity definition, that x minus x naught is less than delta implies f of x minus f of x naught is less than epsilon, except this time the delta can depend only on epsilon and nothing else. Now, it's not hard to prove that if f is continuous on a closed interval, on a closed interval, AB, if and only if f is uniformly continuous on that interval. So continuity on a closed interval immediately gives you uniform continuity. For intervals that are not closed, and if we're working on the whole of the real line, then if the function is uniformly continuous, well then it's continuous, but not necessarily the other way around. For example, if we look at the graph of 1 over x, which looks like this, just on the half open interval 0 to 1, so I'm excluding 0 but including 1, then it's pretty clear that this can't be uniformly continuous, because as I get closer and closer to 0 here, then points that start out very close together are not going to end up terribly close together unless I specify that in terms of how close I am to 0 here. In other words, this difference here will depend on this delta here is going to depend on my x naught, on my x1 and x2. So if you've got a function that's continuous but the interval is not closed, then you don't automatically get uniform continuity. Now I'm going to do a few examples of exactly how this works to show you that it looks a bit scary when you first see all this, and I'll show you some examples to show you that it's not in fact all that difficult to apply the definition. So here is the first example of this one. So a nice simple one, f of x is 2x plus 3. This is about as hard as I would expect you to be able to do with this uniformly continuous stuff. I'll do some other examples as well, some slightly harder ones, just to show you how it works, but I'm not going to expect you to do two exotic examples with these. Okay, so I want to show f is uniformly continuous. So here it is. We put epsilon, given epsilon bigger than 0, we put delta equal to I'm not sure yet. Then if I take x1 minus x2 is less than delta, so we start off with that. Then I want my f of x1 minus f of x2, I need to squeeze less than delta. And I need the delta to depend only on epsilon and nothing else. So I just substitute it in, so I get 2x1 plus 3 minus 2x2 plus 3. Now the 3's cancel out, so I get 2x1 minus, and this is absolute value of all this, so I get absolute value 2x1 minus 2x2. You can take a 2 out of that, which is the obvious thing to do. And now again, I look back, I know that x1 minus x2 is less than delta, so this is less than 2 delta. I wanted it less than epsilon, so I just choose this equal to epsilon, and then before anyone looks, I go back and fill in the gap. I need delta to be epsilon over 2. And the delta depends only on epsilon, nothing else. So 2 points that are within delta of each other, where delta depends only on epsilon, given epsilon, then the difference between their function values is less than epsilon. So therefore f is uniformly continuous. Now, second example here, I mentioned if you've got and this works everywhere, this works on the whole of the real line. If we've got a function on a bounded interval, so we're going to take the function x on x plus 1 on the interval 0, 3. This function is continuous on this interval, but we need to show that it's uniformly continuous on the interval from 0 to 3. This is a slightly harder example. Okay, so we just go through it with you. So given epsilon bigger than 0, we're going to put delta equal to something. Not sure what it is yet. Then if I take 2 points, x1 and x2, that are within delta of each other, and I look at the difference, f of x1 minus f of x2. So f of x1 is x1 on x1 plus 1. F of x2 is x2 on x2 plus 1. And clearly I'm going to have to put these over a common denominator. So I multiply these together, and I've got x1 times this one minus x2 times this one. So I just put those two terms over a common denominator. Now I get x1, x2 minus x2, x1, that cancels out. So I get x1 minus x2, absolute value. It's actually absolute value of the whole thing. I should make it absolute value of everything. Now we know what we can do with the top. The top's less than delta, so that's okay. It's the bottom that's a bit of a pest here, so I'm going to just look at the terms on the bottom. Now we know that our x1 and x2 are somewhere inside this interval. Our x1 and x2 are somewhere inside this interval. In particular, x1 is bigger than, sorry, I should say bigger than 0, because we're on the interval there. So x1 is bigger than 0, and that means x1 plus 1 is bigger than 1. And when I turn these upside down, I'm going to get 1 over this is, so this is bigger than 1. So 1 over x1 plus 1 is less than 1. So just let me go through that again, because I've got the numbers slightly wrong here. So x1, there's my x1, it's bigger than 0. So when I add 1 to it, because I'm keeping my eye on this thing here, That's going to be bigger than 1, adding 1 to both sides of this. And then when you turn it upside down, it flips the inequality sign around. So you get 1 over this is less than 1. And then the same argument works for x2 plus 1, because x2 is bigger than 0, so same argument works. So 1 over x2 plus 1 is less than 1. So finally then, putting that back in here, that means the product of these two is less than 1. This one then, so f of x1 minus f of x2 in absolute value is less than, the top is less than delta, and these are both less than 1, and that's just delta. We wanted it less than epsilon, so I'm just going to put delta equal to epsilon, and I go back and fill in the gap, and we can put an epsilon there. So that shows that this function, which is continuous on this closed interval, is in fact uniformly continuous. Now that's a slightly harder example, and it's not dissimilar to some of the things we've been doing before. So I'll leave that example there, and we'll continue this in the next recording.